Okay, what we saw earlier was that you can plot impedance as Bode plot or as Nyquist plot. Bode plot where you show magnitude and phase as a function of frequency. Nyquist plot where you show the imaginary part plotted versus the real part. Okay. Once you have data, can we identify which circuit will be suitable to model this? That's first part. Let us say we realize that this circuit can be used to model the particular data which looks like a semicircle here in the Nyquist plot. Next is, can we find the value of R1, R2 and C2? Third, after we get the values, how do we interpret it? What is the meaning of C2 being 10 microfarad per centimeter square, 20 microfarad per centimeter square? What happens when R2 is 1000? You do another experiment with slight change in conditions, it becomes 1010. How do we interpret that? Okay. That is one set of analysis. So, we have to get circuit parameter extraction, and we can use commercial software, free software, you can get it. Another aspect is, can we say this impedance has come from this reaction? Can we identify a reaction which will give rise to this impedance? We can say this impedance would have come from this circuit. Similarly, we should be able to say this impedance can arise from this reaction. So, an example is Fe2 plus becoming Fe3 plus with an electron. That is one of the simplest reactions that is used. Second, I have not given the values here, but let us say this has forward rate constant as k1, reverse rate constant as k minus 1. Can we find the values of k1 and k minus 1? It is actually a function of potential. So, we should also be able to tell what is that function. Usually, we would write it as k1 as k10 exponential v1 e k minus 1 k2 if you have multiple reactions, just like you have R1, R2, C2, and you can get the values. Here you should be able to say what reaction can give rise to this impedance spectrum and what are the values of those parameters. So, here I want to pause and show you few other techniques. Okay. EAS is normally referred to as a versatile, powerful technique. If you look at the books, if you look at the publications, they would say it is very powerful. And in some cases you would also see people writing that all the information about the system can be captured by EAS. It is not exactly true. What they mean is, if the system is linear and if you have the information from 0 frequency to infinite frequency, then you can reconstruct how the system will behave for any perturbation, any form of change in potential. So, it is essentially saying, I know how the system behaves from 0 frequency to infinite frequency. So, if you tell me I am going to apply a triangular wave, if you tell me I am going to apply a rectangular pulse, then I can reconstruct it using a method called Fourier series. And in Fourier series you can add multiple sine waves to reconstruct a particular shape, periodic. Then you can basically say, by adding the responses I can get the result. But then electrochemical systems are usually not linear and this will not always work. Okay. Here I want to pause and give you an idea of few other techniques. There are many techniques. So, you have some idea of what you get in other techniques. Normally, if you run an experiment, you will first measure the open circuit potential. That is without applying any potential, you just measure what is the potential between the reference electrode and the working electrode. You have 0 current and it will vary as a function of time. Sometimes it stabilizes quickly, you get more or less constant value. Sometimes it changes because the interface changes. It is possible that the electrode dissolves, that means the electrode surface area will change. The concentration of the solution species near the electrode will change because it is dissolving. Or some contamination from the liquid can adsorb on it. Sometimes it may not be a contamination, it may be something you deliberately introduce, it may adsorb on it. So, the potential will change if the electrode surface or the solution changes. Another experiment that is commonly used is called voltammetry. Voltammetry is basically potential and current. We will control the potential as a function of time, we will usually vary it. Okay. It is given at a particular sweep rate, we will say 10 millivolts per second. 100 millivolts per second, 1000 millivolts per second, 1 millivolts per second. Now, if you scan from one potential to another potential at a particular scan rate, that is called linear sweep voltammetry. It is linear, you are sweeping the potential and measuring the current as a function of time. You would normally plot it as current versus potential, current density versus potential. Now, I want you to remember this. If you take an instrument and select LSV or cyclic voltammetry, the instrument will change the potential, measure the current and plot in a particular format, usually this format. If you want to interpret the system meaning the electrode and liquid, they have to be stationary. Meaning for cyclic voltammetric interpretation, the liquid should not be moving, the electrode is not rotating, it is a stationary electrode. That means when you change the voltage, let us say some reactant comes from the liquid and reacts with this, forms a product and goes out, when the potential becomes more and more, let us say one of the reactions, either forward or reverse reaction, okay, it is becoming more and more favorable, then species will come, react and form the product and go out, the concentration of the species at the interface will change. So, cyclic voltammetry, if you do that linear sweep or cyclic, it would increase, and because it becomes diffusion limited, it becomes lower current. And then if you go in the reverse, it is going to come like this, it is again going to take a reverse after this. So, it is like potential versus time, potential here versus time, potential will increase, decrease, come below the original potential possibly, and then go up and come down again. When it is stationary, diffusion will also play a role, and most of the interpretations in the book will use that it is stationary. Now, it is possible for you to rotate the electrode and click cyclic voltammetry. You will get the data, it will not look like this because diffusion will not play a role. So, you have to run the experiment correctly. The software does not know whether you are rotating the electrode or mixing the fluid or not. So, you have to conduct the experiment correctly, it is in your hands, then you can interpret using the standard methods. There is another technique called potentiodynamic polarization. So, in cyclic voltammetry, typically you will specify 20, 50, 100, 200, 1000 millivolts per second. You can also specify 1 millivolts per second, it will still run correctly. So, in cyclic voltammetry, what happens is you have potential changing quickly with time. The capacitor, double layer capacitor will also contribute to the current. You have capacitance, you change the potential quickly, current in a capacitor is going to be given by this function. So, if potential changes quickly with time, the dE by dt is a large number. So, this will become perhaps significant number. Total current is due to the reaction plus this capacitance. The reaction may be kinetics limited, it may be diffusion limited, depending on how fast the kinetics are, how slow or how fast the diffusion is. Now, the next technique called potentiodynamic polarization, from the software point of view, you would again specify a scan rate, potential will change from one to another value at a scan rate given by us. Usually it starts at a potential and ends at another potential, it is similar to LSV, linear sweep voltammetry. Again here you have to rotate the electrode if you have the facility at as high a rate as possible, or you have to mix the solution. Sometimes in corrosion cells they will not mix the solution, they will have two electrodes at a given space and they will run the technique as potentiodynamic polarization, and they will interpret the data assuming diffusion is not playing a significant role. It may or may not be correct depending on the system. If there is a significant corrosion, diffusion may play a role. If it is very small, then it may not play a role. So, ideally you should be able to move the fluid well, either by pumping the fluid or using RDE at a high speed. Next, in the potentiodynamic polarization, the software will allow you to specify a scan rate. You can specify 100 millivolts per second. It will run, it is not going to be correct for interpretation of the data. Because in the potentiodynamic polarization, usually people will take this and do a particular analysis where E is plotted here, log of the absolute value of the current is plotted here, and they would do a particular extrapolation called Tafel extrapolation. That analysis assumes that all the current comes because of reaction. That means there is no contribution from the double layer capacitance, and that is correct only when you scan at a low rate. If you scan at a fast rate, software will do this, the final calculation will not be correct, because the assumption that double layer capacitance does not contribute to this, that has to be confirmed by us choosing the experimental setup correctly and running it correctly. If you want to do the experiment fast, click have a large scan rate, yes it will run fast, but the results you get will have contribution from double layer capacitance. So, you should run it at a slow scan rate. What is slow? Typically it is 1 millivolts per second or less than that. If you have a significant corrosion current, significant current from the reaction, large current from the reaction means very fast dissolution, then you might be able to go at a slightly faster rate and still get the correct results, because still the double layer capacitance will not contribute that much current to the final value. So, we have for example done experiments at 2 millivolts per second, that is going to shorten the experimental time by half. Okay. And if your dissolution is very fast, large dissolution occurs, you do not want to conduct the experiment for a long time because the electrode will dissolve fast. So, you want to conduct for a short time, and at that condition it is okay to have little faster, because you are dissolving fast, the total current is mostly going to be reaction current, very little will come from double layer. But these are the things that you have to know, it is not that the software will force you to do it the right way. you will have to do it the correct way. Only then the interpretation will become correct. There are other techniques. So, in the potential dynamic polarization, as an example, you can have current increasing and then stabilizing after some time. You can have current increasing and decreasing after some time. For example, you can have a reaction where you have a metal, it dissolves and also forms an oxide. The oxide may also dissolve at a particular rate in the solution. When you go to higher and higher potential, the oxide formation rate may be more than the dissolution rate of the oxide, in which case the surface becomes passivated, in which case the current comes down. So, at a superficial level, it will appear like current increases and decreases. This is similar to CV. CV is cyclic voltammetry, but it is not similar to CV. The reason current decreases in cyclic voltammetry, if we conduct the experiment correctly, reason current decreases is because it is diffusion limited. The reason current values decrease here is because it may be getting passivated. So, the interpretation will differ, although the appearance is the same for these two type of experiments.
Won't oxide deposition be hindered on it?
Oxidation of the electrode, for example, if you have titanium, and it is put in HF solution, titanium will get oxidized by water and form TiO2. And if you rotate it, more and more water and HF will come near this. Water is anyway going to be present all the time. So, oxidation can happen because of water, oxidation can happen because of dissolved oxygen. You may have some other oxidizing agent in the solution. I do not have to assume that the oxidation will get hindered because of rotation. Depends on the situation actually. There are other techniques like chronopotentiometry. Chrono is for time. You can have a control current, as an example, plus 20 milliamp per centimeter square, plus meaning oxidizing, can be negative. You can give, for example, deposition of some material, you can give negative current. Again, the convention, European convention would take that anodic is negative, American convention will take anodic as positive. You will have to notice that point correctly. In some of the software, they will also give you an option of selecting one convention. Some of the manufacturer would say this is the convention. Here if you say constant current, potential may increase and then become constant, may decrease and become constant depending on the situation again. If you go at 0 current and suddenly jump to a constant current, the response of the potential will go like this in some cases. Other cases you might form oxide, you might form an oxide on the top of the surface by giving a constant current. Oxide thickness will increase, therefore, the potential needed to maintain the current will keep increasing. So, by looking at the potential as a function of time, here I am giving you one example qualitatively, just drew a graph, but you may have other responses. Based on that, you can interpret this is what is happening in this system. Likewise, chronoamperometry is for a constant potential, what is the response of the current. So, here I would specify a potential and I will monitor current here, I will specify potential and monitor current here. There are other techniques called pulse techniques, where you might control the potential as a function of time, few milliseconds, potential may be at 0, jumps up, comes to 0 after few milliseconds, and it is of course periodic. You specify this time and this time T1, T2, and then this is one cycle, total number of cycles you can specify that, and the current will not instantaneously go up. Current will actually go somewhat like an exponential function. Again, when you switch off the potential, it will not instantaneously come to this, it will decay. Again, based on that you can interpret, it is actually sometimes used in industry for particular way of depositing material. You can even go to high potential, come down to below 0. So, you may deposit something, remove some of it, again deposit something, remove some of it, and continue to do this. In some cases, it will give us a benefit. Normally, we want to deposit a material, we want to deposit to some thickness, we want to finish it fast and then move on to the next sample. But the quality of deposit may not be good. You can run it at a constant potential, you can run it at a constant current. In both cases, many times you would get a sufficiently good quality, it is fine. Sometimes you may not get a good quality because diffusion may be slow. So, deposit something, then give a pass for the material to come by diffusion, again deposit, that is one way. So, that is why you give a pulse, during that time it will deposit, then pass for a few milliseconds, diffusion happens, again deposit, the concentration is more or less same as what it was before. So, the quality of deposit may be better in this way. The reverse sometimes will remove the material. If you give reverse, it will remove, the hope or expectation is that it will remove the material that is not sticking well, that will go first. Material that is deposited and stuck well to the surface will not come out in the short time. So, net deposition rate will be lower, but you will get a good quality material. Of course, you will have to optimize this by trial, and you can see. You do not want to give a large and long reverse pulse, because you are going to remove everything, but occasionally it is beneficial to give reverse pulse also. Occasionally meaning in some systems it is beneficial. Another technique is called quartz crystal microbalance. So, I think many of you may be familiar with what is called piezoelectric material. If you apply a potential to the material, it will deform. So, certain materials like quartz, if you cut in a particular orientation, they have an inherent or natural frequency, and if you apply AC potential at that frequency, it will show resonance. It will have maximum amplitude of movement. If you move away from the resonance, the response will be less. So, if I plot frequency and amplitude of the movement, it would appear like this, and this will be the resonance frequency. If I take a material like quartz, I will make a disc, it is like a coin, and on top of it I can coat gold. You can coat gold, you can coat other materials. On the other side, if I look at it, I will have gold again, and of course, I will have to have leads to take them out and connect. If you visualize, this is a disc I am showing in a large one, it actually looks like a small coin. Part of the disc is coated on both sides. If I apply AC, I am applying potential, so it will oscillate, vibrate. The equipment can measure that. Now, if I coat a material on top, or if I remove some material, the mass will change and the resonance frequency will shift. If I coat a material, it is going to be a little heavier. If you put in a liquid, it is going to be dampened. So, by monitoring the frequency, resonance frequency, and I can monitor it very fast. The frequency is in the range of megahertz, 5 megahertz, 10 megahertz, at least 5 megahertz is common, 10, 20, 30 it is possible to get in high frequency range. That means I can measure it every 100 millisecond. That means every second I can get 10 points, 100 points. At least every second I can get up data which tells this is the mass on this. So, if I deposit a material on an electrode, let us say I am depositing zinc on iron, it is used for galvanizing steel. At a given potential, hydrogen will also evolve on this electrode, zinc will also deposit. The current that I measure is the total current. What we want is zinc deposition, but when we go to that potential, hydrogen evolution will also happen. We want to know how much is the efficiency of this process, means how much current goes into deposition. So, if I use a quartz crystal microbalance and control the potential or current, and on top of it I measure the frequency, I can say how much is the mass change. Hydrogen will evolve as a bubble and go out, it will not contribute to the mass. Zinc will contribute to the mass. I know the total current, from that I can estimate how much should be deposited if everything were zinc. There is a constant called Faraday constant which tells 1 mole of electrons will have this much coulombs. Zinc, for example, we expect it to be zinc 2 plus 2 electron. 1 mole of zinc will give us 2 moles of electrons, or 2 moles of electrons are needed to reduce 1 mole of zinc from the solution. 1 mole of zinc, we know the atomic weight, so we know this much is the mass. So, from the current it is possible to estimate how much zinc should be deposited if all the current has been used for zinc deposition. From the quartz crystal microbalance, you can find out actually how much is deposited to the extent of microgram very comfortably. The manufacturer will claim that you can measure nanograms in this, but microgram you can comfortably measure, meaning even in presence of noise you can measure it well. 0.1 microgram with some difficulty. If you want to measure nanograms, it will work only for a few systems, ideal systems. So, in this case, for example, you would get frequency and current. Initially you apply a potential, you monitor the current, it jumps up and then it is more or less constant. When current is more or less constant, let us pretend in this case that it is depositing at a constant rate and everything is the metal that is depositing. Frequency will keep going linearly. Frequency here is the resonance frequency. You can monitor this and then compare with what you see in the current. And electrochemical microscopy is where you have a small tip, I have not given a graph here, small tip close to the surface in the liquid, and you can scan the tip. Sometimes you can scan the tip, sometimes the sample may be moved using piezoelectric. So, you can move it by micron sized steps or even smaller than that depending on the features that are available. You can move it and then say at these locations this is how much the current. Okay. So, you can see how the surface behaves electrochemically at different locations which are spaced by a few microns. So, if there is a surface heterogeneity, you can find that. If you have an alloy, you can see whether there are like metal clusters or it is really completely alloyed and it is more or less homogeneous. Okay. That is one example of how you can use it.